After I posted my last video, Blue Horseshoe 43 comments that I can't just ignore the ideal gas law and expect to make a fair comparison. And I agree with him, so I want to explore the role of the ideal gas law in the greenhouse effect as carefully as I can. The ideal gas law says that pressure times volume equals the number of moles in the container times the ideal gas constant, which is 8.31 joules per mole Kelvin, times the temperature in Kelvin. Which for a bit I was flummoxed as to how to apply that to an atmosphere where the pressure varies with height, the temperature varies with height, and there's really no clear volume to deal with. What needs to be done, therefore, to make it a sensible equation is to divide both sides by the volume. This turns the equation into one with three well-defined quantities, because we can say at any given height in the atmosphere that we have an average pressure and an average temperature and an average density. Here I have used a fairly commonly used symbol for density, the Greek letter rho. So this value measured in SI units would be in moles per cubic meter. R is in joules per mole Kelvin, which is kilogram meters squared per second squared. So you can cancel out the two of those meters, over mole Kelvin. So you can cancel out that mole. The temperature is measured in Kelvin, so you can cancel out Kelvin. And you can see that it comes out right because pressure is measured in kilogram meters per second squared. That's a Newton divided by the area, meters squared. So you also get kilograms per meter second squared over here. Okay. Anyway, of course the units check out. It's the ideal gas law, so that was superfluous. But the point is that we have this new form of the ideal gas law that says pressure equals the molar density times RT. Now this is going to apply when the atmosphere is in thermal equilibrium. So in the cases where we have severe conditions, fast-moving cold fronts, hurricanes, maybe this doesn't quite apply. And even more strangely, in this very case where I want to apply this equation, look at this. It's not thermal equilibrium. Thermal equilibrium means essentially one thing, constant temperature. In the atmosphere, we have temperatures that go down towards the troposphere at 10 kilometers, then up towards this is the troposphere, and then out in the stratosphere the temperatures rise up again, and then in the mesosphere the temperatures drop again, and then in the ionosphere they go back up again until you get to the thermosphere, which is essentially in thermal equilibrium because it is a fairly constant temperature in the thermosphere. We don't have thermal equilibrium throughout the layers of atmosphere. We have temperature varying as a function of height. But within a small region of the atmosphere, smaller than that actually, but we can say that the small region, and particularly as a function of height in general, we can say that that small region has a uniform pressure, a uniform molar density, and a uniform temperature. So at any given height, we can say that the pressure at that height is equal to the density at that height times the ideal gas constant times the temperature at that height. But we can also say something about the pressure. or something else about the pressure, that the pressure is equal to the sum total of the density of the gas times its height. But actually, since rho we've decided already is a function of height, this is actually going to be the integral of the density at each height times a differential height element from, I guess, h to infinity. Left out a term, rho times the gravitational field times the height. So g, the gravitational field at a given height, is probably, I think, as constant. The gravitational field is going to be gm over r squared. So I'll take the radius of the Earth being 6,371 kilometers, and if you add 10 kilometers or up to maybe 100 kilometers for the top of the mesosphere and ionosphere, you'll get to 6,471. Let's compare the squares of those numbers. Okay, so you can see 6,471 divided by 6,371 squared is 1.03, or the reciprocal 0.969. So the gravitational field up above is about 3% less than the gravitational field at the surface of the planet. So really, the gravitational field is approximately constant throughout the Earth's atmosphere. So we can just make this equation be P. The pressure is rho times g, or integral rho g dh, and we'll just say that rho is a function of height, but g is just a constant. So I think these are kind of two governing equations then. We've got one of them that the pressure is equal to the integral of rho g dh, and the other one that says that the pressure is equal to rho RT. So that essentially gives us, we now have two equations and three unknowns. We have the unknowns are pressure as a function of height, density as a function of height, and temperature as a function of height. The third unknown could be filled in by empirically measured data. Right now, like this diagram I showed up here, we could just measure the average temperature at all of those different heights, and that would give us. So the third unknown could be the third unknown, temperature of height, could be filled in by empirically measured data, and that would be sufficient. Plug that into there and plug that into there, and we could determine explicit functions for pressure and density. I should say average pressure, average density, as a function of the height. Now, I can see on this graph in Wikipedia of atmosphere of Earth, the pressure, the density, and the temperature at any given height. And I think in principle, multiplying or plugging those numbers into the equation should satisfy the ideal gas law. But I think in the context of my current question, the ideal gas law cannot by itself predict these changes in the temperature of the atmosphere in the different layers. Rather, what we'll need is material properties of the gases in the atmosphere, such as its thermal conductivity. I think that the troposphere here is showing properties of an insulator, preventing heat from escaping from the ground. And likewise, the stratosphere up here is acting like an insulator, preventing heat from reaching the Earth. I pointed to the wrong spot. The stratosphere here is preventing heat from reaching the Earth. That heat being generated right in this region, about 40 to 60 kilometers above the planet. I think that's the ozone layer where O3 molecules are absorbing ultraviolet light from the sun. So what this means in the context of what I've already been talking about is that instead of taking the empirical information about measured temperatures, one should, in principle, be able to model all of this without knowing the temperatures, but knowing instead everything about the thermal conductivity of the gases at each height. Well, we talk about insulation in terms of just one number, I think. In British, we talk about the R value, which is the change in temperature divided by the heat flux. So in essence, what I'm saying is that the troposphere has a certain R value, and these different layers of the atmosphere each have an R value, but they have actually two different R values, one for the incoming visible light and a different R value for the outgoing infrared light. So in order to take into account this conductivity, you're going to have to take into account two different values of thermal conductivity, one for the incoming radiation and one for the outgoing radiation. I think, in principle, that if you took all those emission absorption spectra of all of the different materials in the atmosphere, carbon dioxide, ozone, methane, nitrogen, oxygen, etc. If you take the variation of the concentrations of those molecules with height, if you take into account Beer-Lambert's law, which talks about how much radiation is absorbed over a distance, an exponential thing, all of that could be combined to give these two functions thermal conductivities, basically thermal conductivity as a function of height with respect to the incoming heat and the outgoing heat. I think maybe if you took all that into account, you could actually predict the thermal conductivity as a function of height. And once you've got that, you could combine it with the ideal gas law and pressure versus height functions and use it to predict all the data they have here. But that's the essential principle behind the greenhouse gas, that the thermal conductivity of the atmosphere is, for visible light, is perfect. On the way in, the visible light is not, or the atmosphere is basically transparent to it, except to that ultraviolet light there. But on the way out, that light is converted into infrared, and the atmosphere here is basically an insulator, is a heat insulator, which causes the temperature to drop as you go outward. So yeah, I think in summary, yes, the ideal gas law does apply to any given small region of the atmosphere in thermal equilibrium, but to find the variation of temperature, density, and pressure over a span of altitude, you are going to need to take into account the greenhouse effect as an independent variable that you can then plug in to the ideal gas law.